Hello students, we will be reviewing Electrochem in class exercise 1, 2 and 3 in this video. Okay, you might have found some of the questions quite manageable. Let's look at question 1A first. It's a definition question, so directly from your learning objective on students need to know the definition by heart. Of course, knowing by heart is one thing. How do you understand what exactly is standard electrode potential? The standard which we are looking at for H2 Chem, we are always looking at, if I'm going to bring you to the data booklet, you can look at this particular page, standard electrode potential at 298 Kelvin. So it's already written for you that we are measuring it at 298 Kelvin. Of course, from your lecture notes, you also learn several other factors. For example, if you are going to introduce any gases, it should be maintained at 1 bar. If there are aqueous ions in the solution, it should be maintained at 1 mole per dm cubed. Yeah. So with that, when you look at the definition for standard electrode potential, you should be looking at it being the potential difference between the half cell, which you are measuring, okay, and that of the standard hydrogen electrodes. Yeah, so always take note that whatever you are measuring, it should be measuring against standard hydrogen electrodes. And this particular idea is very important. Okay, so and when you're measuring against SHE or standard hydrogen electrodes, it should be under standard conditions. So what are the standard conditions? I think we already mentioned that earlier on. For temperature, it should be at 298 Kelvin. The concentration of aqueous ions, 1 mole per dm cube. And any gases being introduced should be maintained at 1 bar. Okay, so it is therefore not surprising that we have a 1B for you, where you are required to draw a labeled diagram of the electrochemical cell which you will set up to measure the SHE for the dichromate chromium 3 system. Yeah, so remember that any of these questions, whenever we ask you, it should be always it will be always phrased as a labeled diagram, because the diagram is of course very important. The basic drawing of the diagram allows us to see whether you can understand or you understood the concepts being taught to you. Okay, so when you are drawing the diagram, you need to be drawing two half cells. So one is the standard hydrogen electrodes, usually it's on the left, and the other one is the one containing chromate and dichromate. You should be drawing it on the right. Okay, of course, for aesthetic purposes, you should be drawing it using a ruler. Okay, and then of course the next thing you want to draw in will be the electrodes. So for the one on the right, because two of the species are aqueous ions, so you are using a platinum electrodes. Okay, so it's usually drawn using a rectangle. Okay, and then for the one on the left, you need to introduce hydrogen gas at 298 Kelvin and 1 bar. Yep, so I think it's necessary for you to draw in the tube. Okay, so I'm just going to draw it in. It's not going to be very nice, but bear with me a little bit with the aesthetics. Okay, so just going to draw in randomly. Okay, like that. Okay, and then like this. Okay, so I'm going to just leave some holes for the bubbles to be formed, but the bubbles is not necessary. Okay, so I don't really need to draw in bubbles, but aesthetically it will be nicer if I have bubbles. Okay, and then of course I'm going to have a platinized platinum electrodes over here. It's a small one. I'm just going to shade it. Okay, and then of course I'm going to just connect it with the wire. Okay, so just going to connect it all the way with the wire, and then of course flows through a voltmeter, and then I'll just connect it with the platinum electrodes. Okay, and then for the salt bridge, you don't really need to draw in the U-tube, but if you wish to, you can just draw in the U-tube like this. Okay, and then just indicate that this is the salt bridge. Okay, so just label it accordingly. Okay, and then of course the solutions, I'm just going to draw in the water surface, the aqueous surface like this. Okay, yep, so probably I need to leave a little room here so that it can be drawn more nicely. Okay, so I'm just going to draw in the salt bridge in a clearer fashion so that it looks nicer. Okay, yep, and then I'm going to indicate my diagram. I'm going to label it. So this is the salt bridge. So this is a salt bridge. Okay, and this is the platinum electrodes. Okay, and then this is the high resistance voltmeter. Of course, I can just indicate it to be a voltmeter. Okay, and then of course this is the platinized platinum electrodes. So platinized platinum electrodes. Okay, and then for the rest, I'm just going to indicate it directly. So over here, I'm going to have the concentration of H plus to be 1 mole per dm cube. So H plus concentration equals to 1.0 moles per dm cube. And then over here, I'm going to have concentration of dichromates to be 1.0 moles per dm cube. Concentration of chromium 3 plus to be 1.0 moles per dm cube, and then the concentration of H plus to be 1.0 moles per dm cube. Some of you might ask, where does the H plus come from? If you look at your dichromate chromium 3 half cell, it contains chromium 3 plus, H plus, and dichromate. Yeah, so it will be good to include H plus as well. Okay, and then I'm going to introduce hydrogen gas, okay, at 298 Kelvin and 1 bar. Okay, just make sure that you indicate everything and you label it properly. Yeah, so if you have done that, there shouldn't be a major issue in you getting the full credits. Okay, then next, for part C, in the above electrochemical cell setup, label the plus and minus at each electrode. Okay, now we do understand from our standard reduction potential value that dichromate to chromium 3 is a spontaneous process at 1.33 volts. Yeah, so that means that at the half cell on the right hand side, which is the dichromate chromium 3 half cell, the dichromate will always be taking in electrons from the platinum electrodes in order to be reduced to chromium 3 plus. So because it's always, the process that's spontaneous will always be taking electrons from the platinum electrodes, it will take on the plus charge because it's the electrode where electrons are being lost. Okay, and then of course over at the standard hydrogen electrodes, electrons is being so-called produced because the reduction, or rather the oxidation of hydrogen at the electrode will produce H plus, and this is accompanied by an electrons. So it's actually electron rich over at the platinized platinum electrodes. Yeah, remember that this is the electrodes where oxidation is taking place. Okay, so it will take on the negative charge, or rather it will take on the negative polarity. Okay, so with that, you know that the half cell, or the SHE, that is performing the oxidation will be the one where electrons is being produced, and it will flow over to the cathodes where reduction of dichromate to chromium 3 takes place. Okay, so I have labeled them accordingly, so you just check against your own answers. Okay, next we'll look at question 2, okay, where one of the first batteries invented 1836 by the British chemist John Frederick Daniell. So this is the Daniell cell. Okay, it consists of an earthenware vessel. So you have an earthenware vessel over here, and then it's labeled for you already. You have a zinc electrode over here, and then it's filled with zinc sulfates, and then this whole vessel is being partially immersed into a copper pots containing copper sulfates. Okay, so question is, you're supposed to deduce the half reactions that occur at each electrode. So do take note that this is a battery. Okay, so the zinc electrodes again will take on the negative polarity because zinc is a more reactive metal as compared to copper. Yeah, so with that, you know that zinc will be oxidized in the process. So I'm going to just write out the balance equation. So zinc, or rather the balance half equation, the zinc electrodes will undergo oxidation to give us zinc 2 plus aqueous, and then plus 2 electrons. Okay, and then the electrons will flow over to the copper cathodes, where copper 2 aqueous will take in the 2 electrons and be reduced to solid copper. Okay, yeah, so you'll notice that the zinc electrodes will become smaller and smaller, and the copper pots will have some deposits at the sides. Okay, then question is, in which direction will the electron flow in the external circuits? Yeah, so as mentioned, it will flow from the zinc to the copper electrodes. Yeah, so in this case, from zinc electrode to copper electrodes. Then next, for part C, what voltage would the voltmeter show in the above cell? Yeah, so since we are given it to be in standard condition, 1 mole per dm cube. Yeah, so if I'm going to perform the calculation, if you just look at your data booklets, the copper to copper is plus 0.34 volts, and then zinc to zinc is minus 0.76 volts. So zinc is the more reactive metal as compared to copper. Yeah, so therefore if I'm going to calculate the E cell, okay, it will be E reduction. Okay, so that will be copper to copper minus E oxidation. So that will be zinc to zinc. Okay, so I'm going to get plus 0.34 minus 0.76. So I'm going to get plus 1.10 volts. Yep, okay, so that's pretty straightforward. I think it's quite similar to some of the lecture exercise you have in the lecture notes. And then for part D, which component in your diagram in 1B performs a similar function to the earthenware vessel in the Daniell cell? Okay, so you notice that the labeled diagram over here, right, lacks one labeling, although they label the earthenware vessel. Yeah, so the labeling that is missing is the salt bridge. Okay, so yep, your earthenware vessel behaves as the salt bridge. Why does it behave as the salt bridge? Because the earthenware contains minerals, which could usually be ions, could be inert positively charged ions or negatively charged ions. So whatever happens, the ions will then diffused into the appropriate half cell in order to maintain electrical neutrality. Okay, so salt bridge will be the answer for part D. Okay, yeah, so with that, I think we can move on to the next in-class exercise 2. Yeah, so this particular in-class exercise move on to allow us to use the E cell to predict spontaneity, and then of course to understand the limitations, and of course to construct redox equation from relevant half equations. Okay, so first of all, we were told that the architectural and other models are made from brass. It might not be something which you have learned in H2 Chem, but in secondary school you would have learned that brass is an alloy. Okay, that is a mixture of copper and zinc, right? And then okay, so you were given some chemistry over here, like for example, I can remove the unprotected brass by etching. Okay, so yeah, so I mean, you can read about it, or if you're interested, you can find out more. Yeah, but if you go to the question proper, you were told that when a piece of brass is placed in dilute hydrochloric acid, only one of the metal present dissolves. So write an equation for this reaction. Yep, so well, if one of the metal dissolved, that means that the metal will get oxidized. Yeah, so therefore we will be choosing, I mean, let's say if you're not familiar with the reactivity series which you have learned in secondary school. I mean, I shouldn't be mentioning reactivity series, but in secondary school you are familiar with the reactivity series where you learn that any metal above hydrogens will get oxidized, any metal below hydrogen will not react with acids. Okay, and I believe you do know that zinc is above hydrogen and copper is below hydrogen. Yeah, of course, when we look at the standard reduction potential, zinc to zinc is negative 0.76 volts. That means that zinc has a tendency to be oxidized to zinc 2. copper to copper is 0.34 volts. So that means that copper has a lower tendency to be oxidized to copper 2. Yeah. In the presence of H plus, of course. Yeah. So with that, I think you can easily predict that the species or the metal that is undergoing the oxidation is zinc. Okay, so zinc plus hydrochloric acid, 2HCl equals, okay, I'm going to get zinc chloride, okay, plus hydrogen gas. So hydrogen gas is being given off, so you'll notice that you get colorless, odorless effervescence. Okay, yeah. And then use the data booklet to explain why one metal dissolves and the other one does not dissolve in dilute hydrochloric acid. Okay, so you need to flip over to your data booklet. You need to record down the relevant standard reduction potential. That includes copper to copper at 0.34 volts and zinc to zinc at minus 0.76 volts. Okay, as well as the one involving hydrogen, okay, over here, which is 0.00 volts. Okay, because that's the standard. Okay, so yep, so there is a need for you to write down the reduction potential of these species. So zinc to zinc is equals to minus 0.76 volts. Okay, and that's of H plus H is 0.00 volts. Okay, and that's of copper to copper is 0.34 volts plus. Okay, yep. So you can simply just do the relevant calculation. So for reaction between zinc and H plus, okay, so let's calculate the E cell. So E cell is equals to E reduction, okay, E reduction, okay, minus E oxidation. Okay, so I'm going to get 0.00 minus 0.76. Okay, I'm going to get plus 0.76 volts. So this is greater than 0 volts. Yeah, so therefore the reaction is spontaneous and zinc dissolves to give us zinc 2 plus, and H plus gets reduced to give us hydrogen gas. Okay, you should be writing that in your conclusion. Okay, then for reaction between copper and H plus, okay, I'm going to do the same thing. So my E cell is equals to E reduction, okay, minus E oxidation, which is copper to copper. Okay, so I'm going to get 0.00 minus 0.34. Okay, so I'm going to end up with negative 0.34 volts, which is less than 0 volts. Yeah, so therefore the reaction between copper and H plus is not spontaneous. Okay, not spontaneous meaning that copper will not be oxidized to copper 2 and you don't observe hydrogen gas being produced. Okay, yep. Then for 1B, the process of etching brass involves dissolving the unprotected brass in a suitable reagent. So in practice, we are using iron 3 chloride until all the unwanted brass has been removed. Okay, so using relevant E0 values explain why both the components of brass are soluble in aqueous iron 3 chlorides. Okay, so we have to introduce one more reduction potential. So if you look at your data booklet, there are several to choose from. You have iron 3, iron 2, 0.77 volts. Okay, you have iron 3, iron negative 0.04 volts. Some of you might be wondering why I don't choose iron 3 all the way to iron, but I chose iron 3 to iron 2. Okay, if you actually work through the whole thing, okay, so for when iron 3 gets reduced to iron 2, maybe we can just do the calculation first, and I just want you to recognize this first. Okay, so the reduction potential for iron 3, iron 2, okay, is plus 0.77 volts. Okay, now the first thing I want you to do is you do the same thing, just repeat the same idea above. Okay, so repeats the reaction between zinc and iron 3. Okay, and then copper and iron 3. Okay, just perform the calculation first. So I'll do that. So E cell is equals to E reduction minus E oxidation. So that will be iron 3, iron 2, okay, minus E oxidation. So that will be zinc to zinc. Okay, so I'm going to end up with 0.77 minus 0.76. I'm going to end up with plus 1.53 volts. Okay, so which is greater than 0 volts. So again, you make the same conclusion. So therefore, zinc gets oxidized to zinc 2, hence it dissolves. Okay, and of course, iron 3 gets reduced to iron 2. Okay, you do the same thing for copper and zinc 3. So E cell, okay, is equals to E reduction, okay, minus E oxidation. Okay, so 0.77 minus 0.34, I'm going to end up with 0.43 volts. Okay, so it's the same old story. Reaction is spontaneous because the E cell is greater than 0 volts. So therefore copper will be oxidized to copper 2, hence copper dissolves. And then because these two are both positive, that is the reaction involving zinc and copper with iron 3, both are positive. So therefore brass dissolve in iron 3 to produce iron 2, zinc 2 and copper 2. Okay, yeah. I think I mentioned before during tutorials that the word soluble has different meaning in chemistry. Sometimes it means a physical process, sometimes it means a chemical process. Over here, the word dissolves obviously means a chemical process that is taking place. Okay, so yeah, and then we have to support it with the relevant E cell calculations. Okay, yeah. Some of you might be asking, why is it that I do not attempt to calculate the reduction of iron 2 all the way to ions? Okay, well, I mean if you feel very strongly, you could do that, but if you try to do that, this is negative 0.44 volts. Okay, if you try to do that, you can replace this with negative 0.44 volts. You'll notice that the reaction is also spontaneous. I'm sure you will try, and then you might notice that lah. So the reaction is spontaneous, right? But of course, if you try using if you replace iron 3 iron 2 with iron 2 iron for the reaction involving copper and iron 3, right? You'll notice that the reaction is not spontaneous. Okay, yeah. So that does tell you one little thing, and in the solution you do not observe any solid ion being produced. Yeah, so that's also a very important idea which you need to be familiar with. Okay, then so therefore, because I don't get any solid ion, then I don't think iron 2 will be reduced all the way to iron. Okay, another overarching principle is that the iron 3 chloride solution is likely to be relatively acidic for iron 3 to be quite stable, and of course for iron 2 to be quite stable as well. Then if iron were ever to be produced, then obviously iron will react immediately with the acidic H plus to produce iron 2. Yeah, so that's kind of like against, I won't say it's against, but even if that happens, then you will still not see solid iron, because iron will immediately react with the H plus to produce hydrogen gas and iron 2. Yeah, so the thing is, in the etching process, you might not observe hydrogen gas, so that kind of like supports the fact that iron probably will not be produced, and even if iron is produced, it will immediately be oxidized to iron 2. Yeah, so all this is related to observations, and I guess you really have to work on etching brass to be able to appreciate that you shouldn't be using the equation involving iron 2 and ions. Okay, then finally, we are at part 2, where we are supposed to write ionic equation with state symbols for the reaction between copper and iron 3. Okay, so we can easily do that. You know that copper solids plus iron 3, okay, iron 3 plus equals, in the process I'm going to produce copper 2 plus, okay, and of course iron 2 plus. Okay, so remember this, I'm not going to get iron, but I'm going to get iron 2 plus. Okay, and of course iron 3 to iron 2, it will take in 1 electrons from copper. Yeah, but copper to copper 2, it will give out 2 electrons. So if you balance the equations, you should have 2 of this and 2 of this. Okay, yeah, so that will be the balance equation which you should be writing for the reaction involving copper and iron 3. Okay, yeah, so with that, we'll move on to in-class exercise 3, okay, where we are going to apply delta G equals to minus NFE to our electrochemical cell, and then state possible advantages of other types of cell. Okay, so over here, question is the direct oxidation of alcohols in a fuel cell represents potentially the most efficient method of obtaining useful energy from a renewable fuel. Okay, so for 1A, the first alcohol to be used successfully in a fuel cell is methanol. So this is the methanol fuel cell. So at the anodes, methanol and water undergoes the following reactions. Okay, so the equation has already been given to you, so you are quite fortunate. You don't have to balance it yourself. Okay, if you are required to balance it yourself, it's also not too difficult. The first thing to recognize is the oxidation state of carbon in methanol. Okay, so if you perform the usual calculation, if you let the oxidation state be x, so that will be x plus 4 minus 2 equals to 0, so x is minus 2. So this is from minus 2 to plus 4. Okay, so from minus 2 to plus 4, it gives out a total of 6 electrons. Okay, and then if you balance off the charge, you need to add 6H plus on the right hand side. Yeah, and then with that, the water will automatically balance on its own. Okay, so I don't think I need to show you how to balance. It is of course possible for the question to test you on balancing. Yeah, but sometimes the equations will be given to the students for simplicity, so that they fulfill the main objective which they wish to test in a particular part. And then the electrons pass around the external circuit to the cathodes. This is understandable because this is a fuel cell. Yeah, so it's a battery. Then the protons move through the conducting polymer electrolyte to the cathodes. Okay, and then where they react with oxygen producing water. So construct an equation for the cathode reaction. Okay, yeah. So in our case here, you have to read the question really carefully, because you can from the phrasing, the protons move through the conducting polymer electrolyte to the cathodes. Okay, so protons be attracted to the cathodes, reacts with oxygen to produce water. Okay, so if you look at your data booklets, you can simply just look at your data booklets and fish out the equations. Okay, so I think the obvious one is over here, oxygen and 4H plus to give you with 4 electrons to give you water, because you are told that the oxygen reacts with the H plus from the conducting polymer to produce water. Okay, so with that, we'll just write in the answer straight away. So that will be oxygen plus 4H plus 4 electrons, and then in the process I get 2H2O. Okay, if you want to, you can write in the state symbols. It's not a problem at all. Okay, then for part 2, hence construct the equation for the overall reaction showing your working. Okay, so this should be relatively straightforward, because this is the reaction at the cathodes. Okay, so what we need to do here is, this is the reaction at the anodes, and then the one below is the reaction at the cathodes. Okay, so we can what we can easily do is simply just multiply the reaction at the cathode by 2, and then multiply the reaction of the anode by 3. Okay, so I will not be bored. I will not bore you the details, so I just multiply directly. So therefore, at the anodes, So anodes, because I multiply it by 2, I'm going to get 2CH3OH plus 2H2O, and then I'm going to get 2CO2 plus 12H plus 12 electrons. And then at the cathodes, okay, I'm going to get 3O2 plus 12H plus, okay, plus 12 electrons, and then I'm going to get 6H2O. Okay, so if I'm going to just perform the addition directly, the electrons will cancel out, H plus will cancel out as well. Okay, so the overall equation, so overall I'm going to get I need to cancel the water as well, so water, I'm left with 4. Okay, so eventually I'm going to get 2CH3OH liquids plus 3O2 gas. Okay, and eventually I'm going to get 2CO2 gas plus 4H2O liquids. Okay, so this is the overall equations which we can derive from the cathode reaction returns as well as the anode reaction given to us. Okay, yeah. Then next, for part 3, the cell is capable of producing an EMF of 1.18 volts using suitable data from the data booklet suggests a value for CO2 methanol electrode reaction. Okay, we can easily do that. Okay, so first I'm going to write out E cell because it's given to us. Okay, and then what happens at the anode? So it's E reduction minus E oxidation. So the cathode reaction is the reduction of oxygen to water. Okay, how do we know? It's given to us. Okay, it's given to us. Not given to us, sorry. We were asked to write it. It's over here. So oxygen to water. Then minus E oxidation. So what happens at the anodes? So at the anodes, we learned that we are looking at this. Methanol gets oxidized to CO2. So this is the CO2 methanol half cell. Okay, yeah. So do we know the values to the E cell? Yes, we were told that is 1.18 volts. Do we know oxygen water? Yes, 1.23 volts. So this is plus 1.23 minus of the CO2 methanol half cell. Okay, so we can easily determine it. So therefore, we're going to calculate this directly. 1.23 minus 1.18. We are going to get plus 0.05 volts. Okay, as our answer. Okay, yep. Then next, for part 4, suggest a possible advantage of using the methanol fuel cell as compared to a hydrogen fuel cell. So what could be a possible advantage? I think we understand that for the hydrogen fuel cell, the hydrogen has to be stored under immense pressure, so maybe close to 200 to 500 atmosphere. So we need very sturdy tank to store it. But for the methanol fuel cell, it is a liquid. Methanol is a liquid, so it can be easily stored and also transport without any difficulty. Okay, yeah, and of course, another advantage I can think of for methanol is that it is much safer to use because its tendency to explode, or even I mean, it is flammable, but its tendency to react with oxygen requires a much greater barrier, okay, as compared to that of hydrogen, because a little bit of hydrogen with the right activation barrier will react explosively with oxygen. Yeah, so in terms of that, methanol is therefore much safer to use as compared to hydrogen. Okay, so that will be a possible advantage we are looking at. Then finally, for part B, we were told that ethanol is also being investigated as a possible fuel in fuel cells. So we are supposed to write the equation for the complete combustion of 1 mole of ethanol. Okay, so our reference point is 1 mole of ethanol, so we have to abide by this. So CH3, CH2OH, Okay, ethanol is a liquid, plus O2. Okay, so you have to be very careful here. And it's always easier to balance the carbon first. So 2 carbon on the left, so 2 CO2 gas being given off. Okay, and there are a total of 6 H's on the left, so therefore 3 H2O. Okay, yep. And then when we balance, we need to look at the oxygen. So we have 7 oxygen on the right, 1 oxygen from ethanol. So therefore we need 3 O2 to balance it. Okay, so this will be the balance equation I'm going to write for B part 1. Then for B part 2, we were asked for we were told that the standard enthalpy change of combustion for ethanol has a value of negative 1367 kilojoules per mole, and the entropy change for the same process is negative 140 joules per mole per Kelvin. Do take note of the difference in the units. One is in joules, the other one is in kilojoules. Okay, so because most of you have not been doing energetics for a long time, sometimes you might make mistake in this. Okay, calculates the standard Gibbs free energy, delta G, for the combustion of ethanol at 298 Kelvin. So this should be straightforward. Delta G at 298 Kelvin is equals to delta H, okay, minus T delta S. Okay, so for delta H, is given to be negative 1367, and then the standard at 298 will be negative 298. Okay, delta S given to be negative 140. Yeah, but this is in joules, so let me convert to kilojoules. So that will be negative 0.140 kilojoules per mole per Kelvin. And then I will take my calculator, punch the values. I should get negative 1325 kilojoules per mole. Yeah, so it's highly exergonic. Okay, negative 1325 kilojoules per mole. Next, we'll look at part 3. Use the equation you have written in part 1 to calculate the E cell for the ethanol oxygen fuel cell. Okay, so we are required to calculate the E cell for the ethanol oxygen fuel cell. Okay, now first of all, this is the equations which we have written for the combustion of 1 mole of ethanol. Okay, now the next thing we need to do is to write out the half equation for the ethanol oxygen fuel cell. Okay, so I'm going to write in red so that it's not so confusing. So we are already given the earlier on we have already sort of balanced the oxygen water half cell. So I'm just going to write it in over here. So that will be O2. I'm not going to write the state symbols. Okay, so just O2 plus 4H plus 4 electrons. I'm going to get 2H2O. Okay, and then what about for ethanol oxygen? Sorry, not ethanol oxygen, but I need to write. Okay, this is the ethanol oxygen fuel cell, but of course when I write it over here, I'm actually looking at the process which involve ethanol to carbon dioxide. Okay, so I should be writing it over here as well. So ethanol, CH3, CH2, OH. I'm going to write in the balance redox half equation, or the balance half equation. So arrow, I'm going to get 2 CO2, okay, plus blah blah blah. Okay, so the first thing I need to do is I need to determine the oxidation states of each of the carbon, but there isn't a need to, because I can simply just take the average oxidation states because it works as well. So there are 2 carbons, so it will be 2x, altogether 6 hydrogen, so plus 6 minus 2 equals to 0. So I'm going to do a quick one, so that will be x is minus 2. So the average oxidation state for carbon is minus 2. The final oxidation state is plus 4. Okay, so therefore each carbon gives out 6 electrons. 2 carbon will give out a total of 12 electrons. Okay, and then I will balance this with the H plus. That will be 12 H plus. Okay, and then you will notice that water will miraculously balance on its own, because I have 6H on the left, I have 12H on the right. Then I will need to add an additional 3H2O, And then you notice that the oxygen will balance on its own as well, because 4 oxygen on the right, and then the 3 H2O gives 3 oxygen, and then ethanol gives 1 oxygen. Okay, so this will be the balanced half equations, which I'm going to write for the ethanol, the oxidation of ethanol to CO2. So in total, it will give off 12 electrons. Then for the oxygen water half cell, oxygen will take in 4 electrons to be reduced to 2 H2O. Yeah, but if we look at 1 mole of ethanol in the oxidation to carbon dioxide, it will give off 12 electrons. Yeah, so therefore the oxygen here, I will need 3 moles of oxygen in order to take in all the 12 electrons. Yeah, so from here we can conclude that the electron transfer is 12. This is very, very crucial in order to help us get our final answer to calculate the E cell. Okay, yeah. So with that, we know that we know the equation. So E cell, oh sorry, not E cell, delta G. Okay, so delta G is equals to minus NF E cell. Okay, do we know delta G? Yes, negative 1325 kilojoules per mole. Okay, so remember to convert it to joules per mole. Negative 1325 multiplied by 10 to the power of 3. Okay, do we know the number of moles of electron transfer? Yes, so that's 12. Okay, do we know the Faraday constant? Yes, just look at it from the data booklets over here, in case you forgot. It's over here, 96500. Okay, so 96500. So that's 96500. Okay, do we know the E cell? We don't know the E cell because this is what we want to calculate. Okay, yep. So from here, I should be able to obtain E cell quite readily. Okay, so if I punch my calculator, I should get 1.14 volts. Okay, so that's the end to the review for in-class exercise 3. In the next video, we are going to review in-class exercise 4 and 5.